So we're going to look at titrations. These are specifically acid-base titrations. Let's start with a strong acid and a strong base. The equivalence point is the point in the titration when the equivalence of acid equals the equivalence of base. So let's keep it simple and have a monoprotic acid and sodium hydroxide. So if you look at a pH curve, let's say that we start with acid and we're adding base. In other words, acid is in our beaker or Erlenmeyer flask under the burette. Sodium hydroxide is in the burette. So on the left-hand titration curve, you're starting with acid and you're adding base. So the equivalence point would be the inflection point in the middle of our curve. And then it plateaus off as you add more base. The graph on the right would be if you are adding acid. In other words, you're starting with base in your Erlenmeyer flask or beaker. And so the pH is relatively high. And then you're adding acid, you get to the equivalence point, and it plateaus off. You need to be able to recognize titration curves. In other words, given a question, if you had a titration curve like the one on the left, you could recognize it as adding base. Given a titration curve like the one on the right, you could recognize it as adding acid. Okay, here we go. Let's look at our question here. Calculate the pH of a solution in which 10 milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar hydrochloric acid. So we're going to calculate the moles first on the first row here. So sodium hydroxide, 0.0100 liters times 0.100 molar. So we get 0.00100 moles of sodium hydroxide. And then let's look at the hydrochloric acid. With 0.025 liters times 0.100 molar, we get 0.00250 moles. So this is a limiting reagent situation. Our limiting reagent is hydrochloric acid. We're going to subtract 0.00100 moles from our sodium hydroxide and from our hydrochloric acid. We get 0 moles of NaOH. It was used up. So it has a final molarity of 0. We get 0.00150 moles of HCl. We put the moles of HCl over the total volume, which is 0.0350 liters. So just a reminder, this is a limiting reagent situation. You will subtract only the smallest number of moles from both sides. And then our final molarity of HCl, we calculate. And remember, the volumes are additive. That's how we get the 0.0350 liters. We convert that into our molarities. We do the calculation. We get 0.042857 molar. And this is a strong acid. So whatever your molarity is of a strong acid, you use that to get your pH. So our pH is 1.368. Okay, let's look at a weak acid, strong base. This is all the same problem. So we're going to start with 1A. What is the pH of 50 milliliters of 0.1 molar acetic acid? So you haven't added any base at this point. You just have acetic acid. So this is an ice table of a weak acid. So let's put in our molarity. Acetic acid is 0.10 molar. We have 0 hydrogen ion, 0 acetate. So fill out your initial. Then we do the change. Minus X, plus X, plus X, and our equilibrium. 0.10 minus X, X, and X. So we're using acetic acid through this entire problem. The Ka of acetic acid is 1.75 times 10 to the minus 5. We set that equal to our x squared over 0.10 minus x. We use the 5% rule, so we simplify it. So now it's x squared over 0.10. And we solve for x. So we're going to get our x as 1.304 times 10 to the minus 3. That's our hydrogen ion concentration. We put it in our pH equation, and we get the pH of 2.88. So this is what we've been doing in the prior chapter. It's just a plain old ice table. So let's look at what we're doing as far as the titration. So we have in our burette our base, sodium hydroxide. You could use any strong base. At this point, no base has been added. The pH is due to the dissociation of the weak acid. So our acetic acid is in our container. I drew it earlier in my picture for you. We would have a pH probe in here, but I didn't want to try to draw that. So if we look at our titration curve at this point, we have 0 base added. So our pH would be pretty low, and it's just due to the dissociation of the acetic acid. Okay, keep in mind this is the same problem. Now we're on 1B. So we're still using acetic acid, and we're using sodium hydroxide. So now we have 50 milliliters of acetic acid, 10 milliliters of 0.1 molar sodium hydroxide. Sodium is a spectre ion. So you're going to fill out your calculation of moles. So why don't you do that? So when you calculate your initial moles, you have 0.0050 moles of acetic acid, 0.0010 moles of hydroxide, and this is, again, a limiting reagent problem. For your change of moles, hydroxide is your limiting reagent. So you're going to subtract 0.0010 moles from the acetic acid, subtract 0.0010 moles from hydroxide, and add 0.00100 moles of acetate. So go ahead and fill that in. Do your calculations to get your final moles. So your final moles of acetic acid is 0.00400. Your final moles of hydroxide is 0. It was your limiting reagent. It's all used up. And your final moles of acetate is 0.00100 moles. You're losing reactants and gaining product. So now you're going to calculate your molarity. You're going to take the moles and put it over the volume. So notice that our volumes are additive. 50 milliliters plus 10 milliliters equals 60 milliliters. So calculate your molarity of your acetic acid, 0.00400 moles over 0.0600 liters. Check to see that you get 0.0667 molar acetic acid. Then also calculate the molarity of your acetate, 0.00100 moles over 0.0600 liters. Check to see that you get 0.01667 molar acetate. So we're calling this the stoichiometry table. You're going to do the stoichiometry table first. So now you will use your final molarity on your stoichiometry table to fill in your initial for your ice table. So if you would please do that right now. So now you're going to do your change minus x plus x plus x and fill in your equilibrium row. So why don't you do that right now? So now we're using acetic acid. We use the Ka of acetic acid. We use our equilibrium row to set up our equilibrium expression. We set it equal to 1.7 times 10 to the minus 5, which is our Ka. Use the 5% rule. Simplify. And then we solve for x. So go ahead and copy this down. Remember that from our ice table, X is the concentration of hydrogen ion. So we get 6.802 times 10 to the minus 5. Plug that into our pH equation. We get a pH of 4.17. Okay, this is still the same problem. And now we're on 1C. What is the pH of 50 milliliters of 0.1 molar acetic acid and 25 milliliters of 0.1 molar sodium hydroxide? So go ahead and do your calculation of initial moles. Fill in your table there. So calculate your moles. You get 0.00500 moles of acetic acid, 0.00250 moles of hydroxide. The next step is our change in moles. This is a limiting reagent. So we're going to lose moles from our reactants. our limiting reagent is hydroxide, and we're going to gain moles for acetate. So go ahead and fill that in, change the moles. So hydroxide's all used up. You have 0 moles of hydroxide. We have 0.00250 moles of acetic acid, 0.00250 moles of acetate. So now do your calculation of your final molarity. Remember, the volume was additive. So for the acetic acid, it's 0.00250 moles over 0.0750 liters. For acetate, it's 0.00250 moles over 0.0750 liters. Our final molarity is 0.0333 molar acetic acid, 0.0333 molar acetate. So this is our stoichiometry table. We do this first. After we have our final molarity, we use that to fill in our ice table. So go ahead and fill in your ice table, initial change in equilibrium. Now, initially we have 0 hydrogen ion, but we do have acetic acid and we have acetate. So after we fill in our equilibrium, we set up our Ka expression. And again, this is all one problem. So our Ka for acetic acid is 1.7 times 10 to the minus 5. We set that equal to our expression from our equilibrium, x times 0.0333 plus x over 0.0333 minus x. We're going to use the 5% rule. So this simplifies, and notice in this case, the 0.0333 and the 0.0333 cancel. So our X is 1.7 times 10 to the minus 5. That's our hydrogen ion concentration. We use the pH equation, and we solve for pH. So if we were doing a titration curve, our next value, we have added some base, and our number is going up for our pH. Okay, 1D, same problem. What is the pH of a solution of 50 milliliters of acetic acid and 50 milliliters of base? So you're going to do your calculation of initial moles. 0.0500 liters times 0.1 molar acetic acid. 0.0500 liters times 0.1 molar sodium hydroxide. So initially we have 0.00500 moles of acetic acid, 0.00500 moles of hydroxide, and we have 0 acetate initially. Okay, so fill in your change of moles. We're losing 0.00500 moles from the acetic acid and from the hydroxide. We're gaining 0.00500 moles of acetate. So we have 0 moles of acetic acid 0 moles of hydroxide for our final moles, and 0.00500 moles of acetate. So fill in that row. So now we're going to do our calculation of our final molarity. We have 0 acetic acid, 0 hydroxide, and we have for our acetate 0.00500 moles over 0.100 liters. Our volumes were additive. So for our final molarity of acetate, we get 0.05 molar. Okay, so after we do our stoichiometry table, we will do our ice table. In this case, we're starting with acetate. Acetate is a weak base. The lone pair on the oxygen will act as a Lewis base. It will attack one of the hydrogens and remove it. So acetate is the base. The conjugate acid is acetic acid. So if you fill in your initial molarity, you have 0.05 for the acetate, 0 for the acetic acid, and 0 for the hydroxide. Then our change is minus x plus x plus x. Our equilibrium is 0.05 minus x for our acetate, x and x for our acetic acid and our hydroxide. Okay, so acetate is a weak base. We have to find the Kb. The Ka of acetic acid times the Kb of acetate is going to equal the Kw. So 1.7 times 10 to the minus 5 times Kb of acetate equals 1.0 times 10 to the minus 14. So we get the Kb is 5.88 times 10 to the minus 10. So use your ice table to set up your equilibrium expression and use the 5% rule. So go ahead and copy that down. Solve for x. Our x is 5.42 times 10 to the minus 6. And remember to use your ice table as your directions. This is our concentration of hydroxide. So from that, we'll get a pOH, 5.266. If we get a pOH, we can solve for pH because pOH plus pH equals 14. So we get a pH of 8.73. Okay, same problem. We're still using acetic acid. We're still using sodium hydroxide. So we've got 50 milliliters of acetic acid and 60 milliliters of sodium hydroxide. So please go ahead and fill in the calculations of initial moles row. Then calculate your initial moles. So go ahead and copy that down. So for our calculation of initial moles, we only have acetic acid and hydroxide. We have 0 acetate. So for our change of moles we once again have a situation where it's a limiting reagent. We're going to subtract 0.00500 moles from our acetic acid. We're going to subtract 0.00500 moles from our hydroxide. So we're losing our reactants, and we're gaining our products, which is acetate. So plus 0.00500 moles of acetate. So our final moles of acetic acid is 0. Our final moles of hydroxide is 0.00100. And our final moles of acetate is 0.00500. So now we have to do our calculation of our final molarity. So go ahead and do that. Keep in mind that the volumes are additive. 50 milliliters plus 60 milliliters, you get 110 milliliters. So for your final molarity of the hydroxide, you should have gotten 0.00900. Oh, 0.00909 you can read. For acetate, 0.04545. So again, this is just a stoichiometry table. We're just setting up our limiting reagent. And then once we have that, we can do another ice table. The beauty of the stoichiometry table is that you use the final molarity from your stoichiometry table to write in your initial row for your ice table. So we've got acetate is a weak base reacting with water. We get a conjugate acid of acetic acid and hydroxide. So the 0.00909 is our hydroxide, so make sure you put that in the right place. Our 0.04545 is our molarity of our acetate. Then fill out the change. Minus X plus X plus X. Then your equilibrium, 0.04545 minus X for our acetate. X for our acetic acid. 0.00909 plus X for our hydroxide. So now that we have our equilibrium values, we will put that into our equilibrium expression. And remember, acetate is a weak base. We're going to use a Kb. So our Kb is 5.88 times 10 to the minus 10. We set up our expression. We use our equilibrium row, products of our reactants. We use the 5% rule and simplify. We solve for X. Our X is 2.94 times 10 to the minus 9. And remember, this is our concentration of hydroxide. We get a pOH, 2.04. From our pOH, we get a pH. So that wasn't so bad.